In this section we're going to look at p-series, which are series of the form the sum from n equals some integer to infinity of 1 over n to the p. And we want to be able to decide for each value of p whether these series converge or diverge. And we've already seen one of these series, namely the harmonic series. We know that the sum from 1 to infinity of 1 over n diverges, since we also know that what happens with the first few terms of a series doesn't influence convergence or divergence in any way. The sum from n equals a to infinity of 1 over n diverges no matter what the a is. Now we're going to use something called the integral test to decide whether these series converge or diverge. And I've stated the integral test here. Suppose I have a series, the sum from 1 to infinity of an, and I want to decide whether it converges or diverges. Then if I can create a function f of x where x replaces n in the formula for an, and suppose also that that function is positive, decreasing, and continuous on the interval from 1 to infinity, then the series does the same thing as the improper integral from 1 to infinity of f of x. In other words, if the improper integral from 1 to infinity of f of x converges, the series converges, and if the improper integral diverges, then the series diverges. So we can rephrase the problem of whether the series converges or not in terms of deciding whether an improper integral converges or not. And sometimes this makes the problem easier. The result is still going to be true if f of x is decreasing from some point on, say from 100 to infinity, as long as there's some number m so that beyond that point the function is decreasing. Let's look at the p-series. Let's try to decide whether the sum of 1 over n to the p converges or diverges for some value of p, and you'll see why this integral test works in the process. We already know about the integral from 1 to infinity of 1 over x to the p. We studied this in detail in the section on improper integrals, and we know that this converges if p is bigger than 1, and it diverges if p is less than or equal to 1. And now we're going to compare the series, the sum from 1 to infinity of 1 over n squared, to the improper integral, the integral from 1 to infinity of 1 over x squared dx, which we know converges. The integral test tells us that because this integral converges, the series converges, but let's try to get some insight into why this works. On the right-hand side, we've drawn the function y equals 1 over x squared, and of course it goes to infinity at x equals 0, but the area under the curve from 1 to infinity is finite, because the integral from 1 to infinity of 1 over x squared converges. And now we can represent the series, the sum of the series geometrically, as the sum of the areas of the orange rectangles in this picture. The height of the first rectangle is 1 over 1 squared, which is the height of the function at the right end point of the interval from 0 to 1. And therefore the area of this first rectangle is 1 over 1 squared because it also has base 1. And the height of the second rectangle is the height of the function at the right end point of the interval from 1 to 2, and it's 1 over 2 squared. So the area of this rectangle is also 1 over 2 squared because its base has area 1. And the sum from 1 to infinity of 1 over n squared is the sum of the area of these orange rectangles. Now, clearly that's the area of the first rectangle plus something smaller than the area under the curve between 1 and infinity. And of course, because that's finite, the sum of the series must be 1 plus something finite, so therefore it converges. Algebraically, we know that this series converges if the sequence of partial sums converges. And the kth partial sum is sk. It's 1 plus the sum of 1 over 2 squared plus 1 over 3 squared, etc., plus 1 over k squared. Clearly we can see that the sum from 2 to k of 1 over n squared is the sum of a finite number of these orange rectangles to the right of x equals 1. This is less than the area under the curve, which is the integral from 1 to infinity of 1 over x squared. So the kth partial sum of this series is less than 1 plus the integral from 1 to infinity of 1 over x squared dx, which is actually equal to 1. This is something we can calculate. So 1 plus this integral is 2. This sequence is increasing because the terms of the sequence 1 over n squared are all positive, and it's bounded above by 2. So therefore the sequence of partial sums as a sequence is forced to converge. So we can conclude that the sum from 1 to infinity of 1 over n squared converges. Note we're not saying that this sum equals the area under the curve here. We're just saying that the sum of the terms beyond 2 is less than or equal to the area under the curve here. Now we know that if p is less than 1, the integral from 1 to infinity of 1 over x to the p diverges. So our reasoning for 1 over x squared is not going to work. And in this case, if I want to calculate the sum of the p series, I go the other way. I show that the sum is bigger than the integral from 1 to infinity of 1 over x to the p. So let's look at the series, the sum from 1 to infinity of 1 over n to the 1/2. And let's compare it to the improper integral, the integral from 1 to infinity of 1 over the square root of x, which we know diverges. So on the right-hand side, I've drawn the graph of y equals 1 over the square root of x. And I know that the area under this curve between 1 and infinity is infinite. And now I draw a series of orange rectangles representing our series, the sum of 1 over n to the 1/2. And the height of these rectangles is the height of the function at the left end point of the base. So the height of the first one is 1 over the square root of 1. The height of the second is 1 over the square root of 2. The height of the third is 1 over the square root of 3, etc. And of course, because all of the bases have length 1, their areas are equal to their heights. And clearly we can see from the picture that the sum of the areas of these rectangles is larger than the integral from 1 to infinity of this function 1 over the square root of x. Since the integral is infinite and the sum of the series is larger than the integral, we can conclude that the sum of the series is infinite or the series diverges. And algebraically we can deduce this by noting that the nth partial sum of this series is bigger than the n minus 1th partial sum, which is the sum of the areas of n minus 1 rectangles on this picture, and that's bigger than the integral from 1 to n of 1 over the square root of x dx. So the area under the curve above these subintervals, which are the bases of the rectangles. And now we see that the limit of the partial sums of the series is bigger than the limit of the integral from 1 to n of 1 over the square root of x dx as n goes to infinity, but this is by definition the improper integral, which we know is infinite. So therefore these partial sums tend to infinity as n goes to infinity, and we can conclude that our series diverges. Let's look at a few examples of p-series and decide whether they converge or diverge. And with this result, it's pretty easy to decide. So our result says that the sum from 1 to infinity of 1 over n to the p converges if p is bigger than 1, diverges if p is less than or equal to 1. And in fact, we can start the series anywhere because the behavior of the first few terms never affects convergence or divergence of a series. Well, here's a bunch of p-series, and we know that the sum from 1 to infinity of 1 over the cubed root of n diverges because this is a p-series with p equals 1 over 3, which is less than 1. And we can also say that the sum from 1 to infinity of 1 over n to the 15 converges, since this fits the description of a p-series with p equals 15 greater than 1. And also at a glance we can tell that the sum from 10 to infinity of 1 over n to the 15 converges because it doesn't matter whether the series starts at 1 or 10, the behavior of those first 10 terms don't affect convergence or divergence. So this series does exactly the same thing as the sum from 1 to infinity of 1 over n to the 15. We also know that the sum from 100 to infinity of 1 over the fifth root of n converges or diverges if and only if the sum from 1 to infinity of 1 over the fifth root of n converges or diverges. And of course this is a p-series with p equals 1 over 5, which is less than 1, so this series diverges.